Have you ever wondered why we're still alive and why Earth hasn't turned into a scorched wasteland after collision with a space rock the size of a skyscraper? And most people think astronomers track every dangerous object in space and that we have a catalog of all asteroids that could kill us and that we're protected, but here's the truth nobody talks about. We track less than 40% of potentially hazardous asteroids, and every month, objects capable of erasing an entire city fly past Earth, and we only learn about them after they've already passed. And in February 2013, an asteroid only 17 meters in diameter exploded over Chelyabinsk with the force of 30 atomic bombs dropped on Hiroshima, and not a single early warning system detected its approach because it came from the direction of the sun from our telescope's blind spot, and we only saw it when the sky caught fire. And 1,500 people were injured from shattered glass and shock waves and panic, and this was an object the size of a bus. So now, imagine what happens if the next one is the size of a football field or a mountain, and by the end of this video you'll understand why our asteroid detection system is a leaky sieve and why the next impact could happen at any moment without the slightest warning. But first you need to know why space is full of invisible projectiles flying straight at us, and why scientists are afraid to talk about this out loud. So why do we even think we're protected, and where did this confidence come from that astronomers have everything under control? The setup started in the 1980s when a group of scientists led by astrophysicist Luis Alvarez proved that dinosaurs didn't die gradually, but instantly, when an asteroid 10 kilometers in diameter crashed into the Yucatan Peninsula 66 million years ago and threw trillions of tons of dust and ash into the atmosphere and blocked sunlight for years, and planetary temperature dropped and photosynthesis stopped. And food chains collapsed, and 75% of all species disappeared within months, and this event is called the Chicxulub impact, and the crater from it is still visible on satellite images as a circle 150 kilometers in diameter buried under layers of sedimentary rock. And when this news became public, the world realized we live in a shooting gallery, and at any moment a bullet could arrive, and the US Congress in 1998 gave NASA a directive to find and catalog 90% of all near-Earth asteroids larger than 1 kilometer in diameter, meaning those capable of causing global catastrophe. And this sounded ambitious and responsible, like humanity was finally taking control of the situation. But here's what's actually happening, and NASA completed the task because we found approximately 95% of killer asteroids larger than a kilometer, and the good news is that none of them will collide with Earth in the next 100 years. But the bad news is this is just the tip of the iceberg, because objects between 140 meters and 1 kilometer in diameter, meaning those capable of destroying an entire country or causing tsunamis hundreds of meters high, number around 25,000, and we've only found 40% of them. And this means that somewhere in space right now, there are 15,000 asteroids the size of a football field or larger flying around, whose orbits we don't know and whose trajectories we haven't calculated, and any of them could be on a collision course with Earth and objects between 20 and 140 meters, meaning those that could erase a city like New York or Tokyo, number in the millions, and we don't track even 1% of them. And the Chelyabinsk meteorite was exactly from this category at 17 meters, and nobody saw it, and it exploded over a city with a population of over 1 million people. Imagine this like Russian roulette, where the cylinder has 1 million chambers, and you only know the location of a few thousand of them. And you spin the cylinder every day and every hour and every second, because Earth moves in its orbit at 30 kilometers per second. And every second we cross a new section of space where there could be objects we have no idea about. And this is the same reason you can safely cross the road 1,000 times, but on the 1,001st time you get hit by a car you didn't notice because you relied on incomplete information and thought you controlled the situation. Dr. Amy Mainzer from NASA's Jet Propulsion Laboratory, who leads the NEOWISE asteroid detection mission, said in a 2021 interview that we live in a cosmic shooting gallery, and most of the time, we don't even know where the next bullet will come from. because our telescopes only see what's illuminated by the sun and located in a certain range of orbits, and everything else is a blind spot. So let that sink in, because the leading NASA specialist on asteroid threat openly says we're blind to most dangers. But that's not even the strangest part, because the problem isn't just that we don't see all asteroids, but that even the ones we do see, we often lose. What happens when an astronomer finds a new asteroid, but then can't find it again? The setup sounds absurd, like how can you lose a rock the size of a skyscraper in space because you found it once and recorded coordinates and calculated the orbit and everything's under control, right? But here's what actually happens. And when a telescope first detects an asteroid, it sees it as a moving point of light against a background of stationary stars, and the astronomer takes several images during the night and sends the data to the Minor Planet Center of the International Astronomical Union, and a computer calculates a preliminary orbit. But here's where the problem begins, because to accurately calculate an asteroid's orbit, you need observations over several weeks or months, and if you only saw the object one night, your orbit is an approximate guess with huge margin of error, and the asteroid could be millions of kilometers away from where you expect to see it a month later. And here's what happens next. And the astronomer tries to find this asteroid the following week and points the telescope at the expected point in the sky. And there's nothing, because the object disappeared, not because it evaporated or changed course, but because the calculations weren't accurate enough and it ended up in a different part of the sky that nobody checked. And this asteroid is now categorized as lost, meaning we know it exists, but have no idea where it is or when we'll see it again. And maybe in a year, or maybe in 10 years, or maybe never, or maybe it'll fly straight at us. And we'll learn about it a few days before impact, when it's already too late to do anything. NASA's database contains over 1,000 such lost asteroids, meaning objects that were detected one or more times, but then disappeared from observations, and some of them are over 100 meters in diameter, and any of them could theoretically be on a collision course with Earth. But we can't check, because we don't know where they are, and it's like if a doctor told you we found a tumor in your body, but we don't know where, and we don't know what size, and we don't know if it's malignant, and come back in a year, and maybe we'll find it. So would you sleep peacefully after such a diagnosis? Asteroid 2010 RF-12, approximately 7 meters in diameter, was discovered in September 2010, and calculations showed it would pass at a distance of about 79,000 kilometers from Earth, which is closer than the orbit of many communication satellites, and astronomers try to track it further to refine the orbit. But the object disappeared, and nobody has seen it since, and we don't know where it is now, and it could return in 10 years and fall into the ocean or into a city or fly past, and we just don't know. Now scale this problem, because every year hundreds of new near-Earth asteroids are discovered, and many of them aren't observed long enough for accurate orbit calculation, and some are lost, and some are found again years later when they accidentally end up in the field of view of some telescope. And this isn't an early warning system, this is a lottery where we hope we get lucky and that a dangerous asteroid will be in the section of sky we happen to be scanning at the right moment, but space is huge and telescopes are few, and every night each telescope can only observe a tiny fraction of the sky. Dr. Alan Harris from the Planetary Science Institute calculated that at current detection rates, we'll need another 30 years to find 90% of all asteroids larger than 140 meters, and that's 30 years, and during that time, any of those 60% we haven't found yet could enter a collision course. So do you understand what this means? Because we're not just playing catch up with asteroids, we're losing. Which brings us to the real question. If we can't even track objects we've already found, how are we supposed to defend against those we know nothing about? But here's what nobody tells you about asteroid detection systems, because they have fundamental blind spots through which an object the size of a mountain could pass, and we wouldn't see it. The setup is simple because most people imagine we have some kind of powerful space radars constantly scanning all the space around Earth, like in movies about military bases where you see all aircraft within 1,000 kilometers on a screen, but reality is completely different. because we search for asteroids using optical telescopes, which are essentially big cameras that photograph sections of sky and look for moving points of light, and this method has huge limitations. First limitation is that telescopes only see what reflects sunlight, and if an asteroid is dark and consists of carbonaceous rocks with low albedo, meaning low reflectivity, it will be hundreds of times dimmer than a bright rocky asteroid of the same size. So imagine trying to see a black cat in a dark room, because even if you shine a flashlight, the cat is almost invisible because its fur absorbs light in exactly the same way dark. Asteroids absorb sunlight, and we only see them when they're already very close and too close for effective warning. Asteroid 2008 TC3, approximately 4 meters in diameter, was discovered on October 6, 2008, just 19 hours before collision with Earth and 19 hours, and this is the first asteroid whose fall was predicted in advance, and scientists celebrated this as a triumph. Because look, the system works, and we predicted the fall. But think about this critically, because the object was so small it couldn't cause serious harm, and it exploded in the atmosphere over Sudan, and its fragments were found in the desert. But now imagine it wasn't a 4-meter rock, but a 40-meter or 400-meter one, and we learned about it 19 hours in advance. So what could we do and evacuate a city in 19 hours or launch an interceptor rocket? Because none of this is possible. Second limitation, and this is critical, because asteroids approaching from the direction of the sun are almost invisible, and when an object moves toward Earth from the sun's direction, it's impossible to see it with ground-based telescopes, because you can't look at the sun without going blind, and your detectors will simply choke on the light. And this is the same reason you don't see stars during the day, because they're there and they're shining, but sunlight is so much brighter it drowns everything else out, and asteroids flying from the solar direction are hidden in the blinding glare of our star, and we can only see them when they've already passed us or when they collided with the atmosphere. The Chelyabinsk meteorite came from exactly there, and on the morning of February 15th, 2013, an object 17 meters in diameter entered the atmosphere at a speed of 19 kilometers per second, which is 55 times faster than the speed of sound from the direction of the sun from the east, where the sky was just beginning to lighten and nobody saw its approach. And the first warning was a bright flash in the sky brighter than the sun, when the object began to disintegrate from friction with the atmosphere, and then the shock wave, because windows exploded within a radius of 200 kilometers and building walls cracked, and people were thrown from their beds by the force of the explosion, and the explosion energy was 500 kilotons in TNT equivalent, which is 33 times more powerful than the bomb dropped on Hiroshima. And this was a relatively small object, so an asteroid 50 meters in diameter, coming from the same direction, would release energy of 50 megatons, which is more powerful than any nuclear weapon ever tested by humanity. Dr. Paul Chodas, who heads NASA's Center for Near-Earth Object Studies, said after the Chelyabinsk event that we have a huge blind spot of approximately 60 degrees around the sun, and any asteroid whose orbit is mainly inside Earth's orbit is invisible to ground-based telescopes most of the time, and we only see such objects in rare moments when their orbits take them far enough from the sun to be observable at twilight or dawn, and even then the observation window is very short. This is exactly why NASA launched the NEO-Y space mission, which is an infrared telescope in Earth orbit that can see asteroids by their thermal radiation rather than reflected light, and infrared sensors see heat and asteroids heated by the sun glow in the infrared range, and this allows detection of dark objects and partially solves the low albedo problem. But even NEO-Ys can't look in the direction of the sun because physics doesn't allow it, and infrared detectors go blind from solar radiation just like optical ones, so the blind spot remains. This is exactly why I create this kind of content, to show you what the news doesn't talk about and what's hidden behind reassuring statement from officials. So if you want more deep dives into real threats facing humanity, subscribe to the channel and leave a comment asking what size asteroid do you think is most dangerous for civilization, and hit like if the thought scares you that we might not see the next threat until it's too late. because this tells the algorithm to show this to people who actually care about our survival as a species and not just random scrollers looking for entertainment. And here's where it gets truly insane because blind spots are only half the problem and the second half is speed. What happens when we detect a dangerous asteroid on a collision course with Earth, but we only have days or weeks to do something? The setup in movies looks heroic because astronomers discover a killer asteroid several months before impact, and world governments assemble and launch a spacecraft with a nuclear warhead and blow up the asteroid or deflect its trajectory, and humanity is saved and credits roll. And it's beautiful and unrealistic, and here's why. To deflect an asteroid, you need to change its velocity by just a few centimeters per second, and sounds simple, right? But the problem is that even a small asteroid 100 meters in diameter weighs about 1.3 million tons. And this is like trying to move a mountain by pushing it with your hands, and you need enormous energy applied at the right point in the right direction. And what's critical is you need time, because the earlier you push the asteroid, the less effort is required, because even a tiny trajectory change made a year or two before collision will make the asteroid miss Earth by thousands of kilometers. But if you detect the threat a week before impact, no technology will save you because the asteroid is too close and moving too fast, and you have neither time to launch a mission nor time for the deflection to take effect. The DART mission, meaning Double Asteroid Redirection Test, launched by NASA in November 2021, was humanity's first attempt to physically change an asteroid's trajectory, and the spacecraft, weighing 610 kilograms, was directed at the double asteroid Didymos, or more precisely, at its moon Dimorphos 160 meters in diameter. And on September 26, 2022, DART crashed into Dimorphos at a speed of 6.6 kilometers per second, and the result was that Dimorphos' orbital period changed by 32 minutes, and this was a triumph because we proved we can change an asteroid's trajectory with a kinetic impact. But pay attention to the details, because the mission was planned for 10 years, and from launch to impact took almost a year, and Dimorphos is a small object, and even for such a small asteroid, it required a spacecraft flying at bullet speed to produce a noticeable effect. Now imagine a real scenario where an asteroid 300 meters in diameter is detected 2 months before collision with Earth, and we don't have a ready interceptor rocket on the launch pad because such rockets don't exist, and NASA needs a minimum of 5 to 10 years from threat detection to deflection mission launch, because you need to design the spacecraft and build it and test it and calculate the intercept trajectory and launch and reach the asteroid, and 2 months wouldn't even be enough to convene an international council and decide who will finance the mission. Asteroid Apophis, 370 meters in diameter, is one of the most famous potentially hazardous objects, and when it was discovered in 2004, calculations showed a 2.7% probability of collision with Earth in 2029, and this caused panic in the scientific community, because 2.7% is a huge probability in astronomical terms, and if the collision had occurred, the impact energy would have been 1,200 megatons, which is like detonating all nuclear warheads on the planet simultaneously, and a city the size of New York would be completely erased from the face of Earth, and the shock wave would destroy buildings within hundreds of kilometers, and a magnitude 6.5 earthquake would affect the entire region. And additional observations in 2005 and 2006 ruled out collision in 2029, but showed possible collision in 2036, and they refined again, and the danger was excluded, and now we know Apophis won't collide with Earth for at least 100 years. But here's the lesson we must learn, because if the 2004 calculations had been correct, we would have had 25 years to prepare, and this seems like a large time buffer. But at the time of discovery, we didn't even have theoretical technology to deflect an object of that size, and DART only proved the concept in 2022, which was 18 years later. Dr. Tom Statler, scientific officer of NASA's Planetary Defense Program, said in an interview after the success of the DART mission that we took the first step and we proved we can push an asteroid, but it's like if a primitive human invented a stone axe and thinks he can now build a skyscraper, because between proof of concept and real planetary defense, there's a gap the size of decades of research and trillions of dollars in investment. So let that sink in, because NASA's leading planetary defense specialist says we're only at the beginning of the path, and we have no real defense. And now add to this the detection speed factor, and remember what I said about lost asteroids and blind spots, because most dangerous objects will detect not 25 years in advance, and not 10 years, but at best a few months or years, and for small asteroids like Chelyabinsk it's days or hours, and in such a time frame nothing can be done except evacuation, and even that won't be complete. Which brings us to the scariest scenario that scientists don't like to talk about publicly, because what if the next threat doesn't come from the main asteroid belt, but from the Oort cloud or from interstellar space? So what does all this actually mean, and why are we still defenseless against a threat we've known about for decades? Let's put all the puzzle pieces together, because we track less than half of potentially hazardous asteroids, and many of those we found we later lost. And we have huge blind spots, especially in the direction of the sun from where objects can arrive without warning. And even if we detect a threat, we have no quick way to neutralize it, because we need years to prepare a deflection mission. And all this assumes the threat will come from a predictable place like the main asteroid belt between Mars and Jupiter, or the Kuiper belt beyond Neptune's orbit. But what if an object arrives from a completely unexpected direction? In October 2017, the Pan-STARRS telescope in Hawaii detected an object moving at a speed impossible for an ordinary solar system asteroid. And this object, named Oumuamua, which in Hawaiian means scout or first messenger from afar, was moving at 26 kilometers per second relative to the sun and was on a hyperbolic trajectory, meaning it wasn't gravitationally bound to the sun and was just passing through. An analysis showed Oumuamua arrived from interstellar space, and this was the first confirmed object from beyond our solar system. And its shape was extremely unusual, because it was elongated like a cigar with a length-to-width ratio of about 10:1, which isn't characteristic of natural asteroids. And even stranger was its motion, because the object slightly accelerated as it moved away from the sun, as if something was pushing it. And this wasn't explained by gravity or solar radiation pressure. And some scientists, including Harvard University astrophysicist Professor Avi Loeb, suggested Oumuamua might be an artificial object and possibly a solar sail of alien origin, and most astronomers were skeptical of this hypothesis and preferred natural explanations. But the fact remains that we only detected Oumuamua when it was already leaving the solar system. And if it had been on a collision course with Earth, we would have learned about it weeks or at most months in advance, which isn't enough time for any action. In August 2019, amateur astronomer Gennady Borisov discovered a second interstellar object, which was Comet 2/Borisov, also moving on a hyperbolic trajectory, and 2 interstellar objects in 2 years. And before this, it was thought such objects were extremely rare and that we might wait centuries before one visited our system. But now it's clear that interstellar objects fly past us regularly. And we just didn't notice them before, because we weren't looking, and statistical models updated after these discoveries suggest that several interstellar objects larger than 100 meters pass through the inner solar system every year, and we only see a few of them. Here's what makes this truly frightening, because interstellar objects move much faster than ordinary solar system asteroids, and Oumuamua was moving at 26 kilometers per second relative to the sun, which is almost twice as fast as a typical near-Earth asteroid, and higher speed means higher kinetic energy on impact, and impact energy is proportional to the square of velocity. So if you double the speed, the collision energy increases fourfold, and an interstellar asteroid 200 meters in diameter crashing into Earth at 30 kilometers per second would release energy greater than 10,000 megatons, which is 1,000 times more powerful than the largest hydrogen bomb ever detonated by humans, and such an impact could trigger global winter and destroy crops worldwide and lead to mass starvation and civilization collapse. And we wouldn't see it coming because interstellar objects come from random directions and their orbits aren't linked to the ecliptic plane where planets and most solar system asteroids are located, and our telescopes mostly scan the ecliptic because that's where most threats are, and an object flying perpendicular to the ecliptic would remain undetected until the last moment. Professor Avi Loeb, in his book Extraterrestrial, published in 2021, wrote that Oumuamua was a gift because it passed us safely, giving us the first opportunity to study an interstellar object, but the next gift might not be so generous, and the next one might arrive at bullet speed without warning from a direction we're not observing, and the first thing we'll know about it is a bright flash in the atmosphere and a shock. Waves sweeping away everything in its path. And remember what I said about Russian roulette at the beginning of the video, and that's why this metaphor is accurate. Now add to this another factor, which is long-period comets. And these are objects arriving from the Oort cloud, which is a spherical shell of trillions of icy bodies surrounding the solar system at distances up to 100,000 astronomical units, where 1 AU is the distance from Earth to the Sun, and comets from the Oort cloud have orbital periods from thousands to millions of years, and we can't track them while they're there because they're too far and too dim, and we only see them when they fall toward the inner solar system and heat up from the sun and begin evaporating and form the characteristic tail. And the problem is that long-period comets move at enormous speeds, up to 50 kilometers per second on approach to the sun, and their trajectories are almost impossible to predict in advance because we don't know about their existence until they're already inside Jupiter's orbit, and if a large comet several kilometers in diameter ends up on a collision course with Earth, we'll learn about it months at best, and we won't be able to do anything. So here's what all this actually means, and the aha moment I promised at the beginning, because the reign of fire didn't start now, and it's been going on constantly for billions of years since the formation of the solar system, and Earth is bombarded by cosmic objects every day, and most of them are grain of sand sized and burn up in the atmosphere as meteors, and hundreds of tons of cosmic material fall to Earth annually, but once every few decades, something the size of a bus falls, and once every few centuries, something house-sized, and once every few millennia, something the size of a football field, and once every few million years, an object the size of a mountain capable of changing the planet's climate and destroying most life. And this isn't a question of if, but when, and when could be tomorrow. Here's what you can do right now, and step one is realize the threat is real, and this isn't the plot of a science fiction movie, and this is statistical inevitability confirmed by Earth's geological record, and impact craters from ancient strikes cover the entire planet, like Chicxulub crater in Mexico and Vredefort crater in South Africa, 300 kilometers in diameter, and Sudbury crater in Canada, and each of them is evidence of a catastrophe that changed the world. And step two is support asteroid detection and deflection programs, because this isn't a luxury, and this is a necessity for species survival, and NASA and ESA and private initiatives like the Asteroid Institute need funding and public attention and political will. And if people don't demand from their government's investment in planetary defense, these programs will be underfunded and understaffed. And step three is spread information, because most people have no idea about the scale of the threat because media doesn't cover this topic, since it doesn't generate clicks or create ratings, and it's too abstract. But the more people learn the truth, the higher the chance we as a civilization will take serious steps for protection. Let's return to the question I started with, because have you ever wondered why we're still alive? And the answer is simple and simultaneously frightening, because we got lucky, and over the last 10,000 years of human civilization, not a single asteroid larger than 50 meters in diameter has fallen on Earth in a densely populated area, and the Chelyabinsk meteorite exploded over a city, but nobody died. And if it had been slightly larger or exploded slightly lower, there could have been thousands of Victims in the Tunguska meteorite of 1908 exploded over uninhabited taiga in Siberia and flattened 80 million trees over an area of 2,000 square kilometers. And if this had happened over Moscow or London, the cities wouldn't exist. And we got lucky, but luck isn't a survival strategy. I want you to think about this because if tomorrow telescopes detect an asteroid 500 meters in diameter on a collision course with Earth in 3 months, what will you do? And will you panic or pray or hope someone figures something out? Or would you prefer to live in a world where we already have a ready interception system, where we track 100% of dangerous objects, and where collision can be prevented years before it becomes a threat? And such a world is possible, and technologies to create it exist or are being developed right now, like space telescopes in solar orbit to close blind spots and improve detection algorithms, and a fleet of interceptor spacecraft on standby and international response protocols. But all this requires money and time and coordination of efforts. And most importantly, it requires people to understand this isn't science fiction, and this is reality we face every day. The rain of fire is falling right now, and most drops of this rain are harmless, but sooner or later a drop the size of an ocean liner or a mountain will fall. And when that happens, the only thing that will matter is whether we're ready. What do you choose? Because will you continue living in the illusion of safety or acknowledge the threat and act? And write in the comments.